Sometimes probability problems can be a little more complex, and we have to take advantage of certain models. So it's a way of organizing our probability, our outcomes, with their probabilities so that I can count up which ones satisfy certain conditions. So we have three different basic kinds of models. One is to use an organized list. So that's really nice when you have things that are easy to kind of make a list of the possible outcomes. You can use area models, which is probably the most common one we'll use, but there are limitations to the area model. Or we can use a tree diagram. So here's some of the advantages of using each one. Now, an organized list is really good when the probabilities are all equal and the list is not too big. So if you have equal probabilities of things occurring, an organized list is really kind of nice, because sometimes people make a mistake of trying to make an organized list when the probabilities are not all equal, and that tends to make causal errors. So that's where you have to be careful. Area model is really nice when you're only working with two events. If you have three or more events, that's when we want to go over and think about using a different kind of model. Now, all these models usually deal with more than one event, and it typically means you're multiplying probabilities as part of the process. Now, tree diagram, well, when we have more than two, but it also works with two events. Sometimes tree diagrams are really nice when the probabilities are also changing based on what happens on the first part. So you have different probabilities occurring after the first event. So maybe if you went up one part of the tree, it has a different response versus going down a different side. That is when a tree diagram is probably even most effective. So we're going to look at an example of each one of these. First, an organized list. So a couple plans to have 4 children. So we're going to have 4 different events right here. There's 4 children, so there's 4 things we're considering. I want to know what's more likely, getting 2 boys and 2 girls, or having more of one gender. So getting more boys than girls, or more girls than boys. Okay, so this is kind of a really good time for an organized list. So I want to show you how to organize this list. So we start with one of the conditions. So let's say they had all 4 boys. Then I can go over and I can start modifying this. Looking at the last one, I'm going to change the last boy to a girl. So we could have all 4 boys. So the first 4 boys, this one would be the first 3 children are boys, with the last one being a girl. Now I'm going to have it where I've now done all the possibilities where the first 3 children are boys. Well, we could have gone boy, boy, girl, boy, or boy, boy, girl, girl. Now at this point, these are all the possibilities where the first 2 are boys. Notice the last column is going boy, girl, boy, girl. This column goes boy, boy, girl, girl. It's going to go again, boy, boy, girl, girl. It's going to be alternating. This next one, we have 4 boys in a row. Now we're going to get 4 girls in a row, because I did all the possibilities with the first 2 are boys. Now I'm going to go boy, girl, and I'm going to repeat what I just got finished doing. So boy, 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 girl, girl, boy, and then girl, girl. So the last column, every other one changes. It's great for when you're looking at boys and girls or heads and tails, things with equal probability. Wouldn't be as good when you're looking at rolls of dice. There's just too many things to list out. Then right here we have boy, boy, girl, girl, boy, boy, girl, girl. Then we have 4 boys and 4 girls. Then we have 8 boys. Now what I'm going to do to modify it for the last part is what happens if my first child was a girl. Well, basically, all I do is going to create the next list is just take this same list and change that B to a G. And I got all 16 possibilities. So here's one thing that helps with counting. 4 children. I have 2 choices for the first child, 2 choices for the second, 2 choices for the third, 2 choices for the last, 2 times 2 times 2 times 2, and for you good math students, that's 2 to the 4th, or 16. All right. So now I'm going to answer my question. So I want to know what's more likely, getting 2 boys and 2 girls, or more than one gender. So let's find this where we have an equal number. Well, I have a boy, boy, girl, girl here. boy, girl, boy, girl. So there's 2 boys, 2 girls. There's another one right here. Another one right there. Another one right here. Right there. And all the other ones, as we look around, have more either boys or girls. So if I count them up, I've got 6 out of 16. So probably getting 2 boys and 2 girls is 6 out of 16. That's 3/8. That's less than half. So the probability of getting more of one gender is 5/8. Because 3/8 plus 5/8 will give me a total of 1. Or I can add up all the other ones and I get 10 out of 16, which are more than one gender. So it's more likely I have more than one gender. Because I went over 50% on this one while it was less than 50% to get 2 boys and 2 girls. Okay, so organized lists are really nice when the probabilities are all going to be staying the same. So you're getting a boy and girl are always the same. Each one is always, going to be probability of getting a boy is a half always. Probability of getting a girl will be a half always. So the probabilities are not different for different combinations. So now we're going to look at area models. Here my probabilities are not all the same. Probability of getting a 6 on this spinner is a half. A 4 is a fourth. Getting a 9 is a fourth. That's not going to keep them all equal. So an organized list would not be a good choice for this kind of a problem. So here's the situation. 2 players are playing a game. Player A spins spinner A. Player B spins spinner B. Whoever has a higher value on the spinner wins. So you got to decide, which player do you want to be? Do you want to be player A or player B? Well, the best way is calculate which one has the better probability of winning. So we're going to make an area model. So I'm going to make a little chart. We had 3 outcomes for the first spinner and 3 outcomes for the second spinner. Now I want to write down the probabilities. Now I'm just going to go from lowest to highest in terms of what the numbers are. So my first number was 4. Probability of getting a 4 was 1/4. Probability of getting a 6, that's my next lowest. That's half the circle. And then probability of getting a 9 would be 1/4. So 1/4 plus 1/2 plus 1/4, that adds to 1. Now you may choose to change this to 2/4, that way it's always out of 4. And that might be a good idea. In fact, I'm going to change things later to make the problem a little bit easier. Now for spinner B, all the probabilities were each 1/3. So to get a 3 is 1/3, to get a 5 is 1/3, and to get a 12 is 1/3. Now the reason why we call them area models is we're going to calculate the area of each one of those little rectangles inside of this little table. So the area of this rectangle is going to be 1/4 times 1/3. That gives it an area of 1/12. That represents the probability the first spinner spun a 4 and the second one did a 3. Now I'd go to the next one. I do 1/2 times 1/3. That gives me 1/6. For the last one, I got 1/2 times 1/4 times 1/3. I get 1/12. Now I'm going to look at this one because everything else is out of 12. So I think I'm going to rewrite that just to make it a little bit easier, because I know I'm going to be adding my fractions, and it's much easier if I have everything as a common denominator. So I think I'll just change this to a 2/12. So 1/6 is equal to 2/12. Now I could have fixed that from the beginning by making this 2 out of 4, and that way all my denominators were the same going across. That may make the problem a little bit easier sometimes. The choice is to use decimals, but be careful with the 1/3. You're going to have to use 0.3333. And then multiply them out, and you can fill them in. But then maybe carry out 4 decimal places to be safe. Well, if you notice, each of these are 1/3 also. So my probabilities for this middle row and the last row are still going to be the same as the other one. Okay, so now I've filled it all out. Now, if you actually added up every single one of these fractions, if I went around and we added them all up, I'd have 3 4/12, 8/12, 12/12. If I add them up, it should total 1. The area of this entire rectangle has a total area of 1. That's a check to make sure you didn't make an arithmetic error in the process. Okay, I want to find out which player should I be? So let's look at the probability that player A wins. I'm looking at spinner A. So I got to look at my numbers, and when this number is higher than the other spinner, I'm going to highlight it. So the first one, well, if I spun a 4, this guy spun a 3, well, that one wins. 6 beats 3. 9 beats 3. Well, 3 was the lowest on the other wheel, and everything's won on spinner A for that case. Now, if I go over to here, well, 4 does not beat 5, so I can't fill that one. But 6 does. 6 beats 5. And then 9 beats 5. And then I get down to 12. Well, 12 is bigger than all the other ones. So those are all my possibilities that player A wins. Now it's got to add up all of my fractions here. So I've got 1/12 plus 2/12 plus 1/12 plus 2/12 plus 1/12. Add up all your numerators. I get 3, 4, 5, 6, 7 out of 12. Well, 6/12 is 50%, so 7/12 is over 50%. So probably the A wins is 7/12. That means B winning would be 5/12. So in this case, I'd choose player A. So you have to kind of make a good logical argument. You can't just simply say, I would choose player A because I think he's going to win. You need to give evidence. Just choosing a player is not going to give an adequate response to a problem of this kind. Okay, that's an area model. Area model is probably a little bit easier for most students to use. If fractions freak you out, change them to decimals. Work with decimals. That's okay. We're more concerned about you understanding the concepts as opposed to whether you can manipulate fractions. Okay, let's say we're doing a tree diagram. So I'm going to use the same spinners, but I'm going to change the rules this time. So this time, we're going to take the two numbers, we're going to add them together, and if the sum is even, player A wins. If the sum is odd, player B wins. Now, which player would you want to be? Well, let's do it with a tree diagram this time, because this way I can add the numbers together at the end of my tree to see whether it's even or odd. So I'm going to start with player A. Well, there's 3 possibilities. So this is spinner A. I'm going to list our possibilities now. Well, I could have done a 4, a 6, or a 9. Probability of getting a 4 was 1/4, a 6 was 1/2, and a 9th was 1/4. Now, after I've done that, I'm going to have to branch off a branch on each one of these to represent spinner B. Spinner B has 3 possible outcomes. There are 3, 5, and 12. And each of those has a probability of 1/3. Now, it's going to be the same for each one of these. So I could just put the same tree each time. Now I'm going to add my numbers. I get 4 plus 3 is 7. That's going to happen 1/4 times 1/3, 1/12 of the time. So again, you're still multiplying your probabilities. Then I have 4 plus 5. That's going to give me a total of 9. 9 happens 1/12 of the time. 4 plus 12 is 16. That happens 1/4 times 1/3, 1/12 of the time. So they were all 1/12. Now I've got 1/2 times 1/3. So to get 6 plus 3 gives me a total of 9. That's going to happen 1/6 of the time. But again, I'm going to change to 2/12 just to make it a little bit easier to add my fractions. 6 and 5 is 11. That happens 2/12 of the time. And then 1/2 times 1/3, again, this would be 1/6 or 2/12. I get 6 plus 12 is 18. That's my result here. On the last column, 9 plus 3 is 12. That happens 1/12 of the time. 9 and 5 will give me a 14 as a sum. That's 1/12. And 9 plus 12 is 21. That's 1/12. So again, let's look at player A. So player A wins if the total is even. So let's highlight all of my even ones. Well, I've got an even one here. I've got an even number. That's not even. That's not even. Right there. Right here. And right there. So let's add them up. We have 1/12, 2/12, 1/12, and 1/12. That's 2, 3, 4, 5. That's 5/12. This time it's less than a half. So this time player B has the advantage. So you can make it actually a fair game by just alternating back and forth, whether you play it where the higher spin wins or where you use the even-odd rule. So that way you can actually make this a fair game if you combine the two different rules.